So today we're going to talk about what is light gauge steel. Light steel framing is galvanized cold form steel, uses the primary structural components which can be assembled as prefabricated panels, and those prefabricated panels can be made into modules, so like building bricks, but more room-sized building bricks rather than individual breeze blocks or Lego bricks. I do use a Lego analogy quite a lot, and the sharp-eyed might have noticed some Lego behind me in the office here. I'm an adult fan of Lego. I do believe it's good mental health practice for a form of meditation, etc. But it's also a fantastic example of being able to combine the same objects but in different arrangements to make different finished objects. So, for example, a Lego brick is universal, has standard sizes and components, but then they can be rearranged into all manner of various things, from Christmas trees to racing cars to characters from films. And it's the same with light gauge steel, in that it's a standardized components, 70mm deep, 100mm deep, 300mm deep studs with flanges, but they can then be assembled into hospitals, houses, etc. We have some examples here. This is all using an 89mm C section, so that's 89mm deep, and with a 40mm flange in this particular instance. But we've used it as wall studs, we've used it as lintels, we've used it as trimmers, bigger lintels. You see a small example there of an infill panel. So it uses lots of the same component in different configurations to produce different parts of the building. And underneath this wrinkly tin, this is a product called Lewis deck, which is a form of composite metal decking, but not so much the Kingspan, SMD, etc. Very deep, 200-300mm deep slabs. This one's 50 deep, so it's much lighter and much simpler, but is another good example of how light gauge steel, thin formed steel, cold formed steel is used in construction in a variety of methods. So the next point is that this is new, is it? This prefabrication, this offsite construction? Not really. What the Roman forts, the Eiffel Tower, and post-World War II housing have in common? Any thoughts?
I suppose the Eiffel Tower is made out of prefabricated steel sections. World War II housing needed to be quick, so again, made out of prefabricated shapes, like a template design. So basically rinse and repeat to get up quick. Roman forts, same kind of thing, conquered most of Europe, and they need to do that quick. So I'm guessing the forts all follow the same kind of template.
Yep, exactly it. They were all prefabricated. So when people say that this is new and it's scary, and the thing with construction, as perhaps you found already, is that if great granddad didn't do it, then it's new and scary and different, and you know, we don't want to be doing different in construction. We're conservative with a very small c, not a political stance. It just, in the very English definition, we don't do new. And so I often joke that if a Roman builder, a Roman centurion, was to magically appear today in 2024, he would, or she would, be able to start work on site straight away, because they had concrete, they knew about prefabrication, things haven't really changed since then, which is kind of frightening. The image that we're showing is, to my eyes, a modular building. It's raised off the floor, it's on pad foundations, it's got side beams, it's got floor joists, it's got braced walls. It's actually a grain store. It's 17th century from memory, and it's at a National Trust property in the south west, whose name I forget, but I do have the details. If people are really interested, I can find them and send them on to you again. It was on these little feet to stop rats being able to get into the grain store, and the ventilation under the floor between the joists, etc., was to keep the air circulating, to keep the grain dry. But the point is, it's from the 1700s. It's not new. It makes great granddad look, you know, young and new, doesn't it? So those arguments of, oh, it's a bit different, isn't it? No, it's really not. It's just that we've forgotten about it. It's so old, it's new again, which is a common thread of life, isn't it? Fashion, etc., gets recycled. So we'll run through a quick history of offsite or prefabrication. We're going to jump forward to the 1800s when a Henry Manning developed a pattern book of portable cottages for export from the UK to Australia with the gold rush, etc. So 1837, again, it's fairly established. Eiffel Tower, as you mentioned, it was a temporary structure, and it was built using prefabricated iron elements, and that was in 1889. We'll jump forward another 20 or so years. Another catalogue company from 1908 to 1940, which was around the time of the Second World War, lack of staff and need, etc. At that particular point, so towards the end of the war, dropped off. But they were producing 75,000 homes over a 30-year period from 400 house types. So again, it's not new. I often see points that it's planning, it's this, it's that, it's factories don't work. It plainly does. For 30 odd years, it's worked. We need to work out why. IKEA, we all know IKEA, teamed up with Skanska, another Swedish company, but this one construction, to do Bocklock houses, or Bocklock houses. That unfortunately has died a death, but 2001, I joined the industry, so 23 years ago. In 2010, a 57-story hotel was built in just 19 days in China. 19 days. Now, that is a bit of a marketing tool, phrase, etc. It didn't take 19 days from somebody having an idea of let's build a hotel to it being built. But it took 19 days on site, from breaking grounds to turning up. The record another record that I'm aware of that is relatively impressive are McDonald's drive-through eateries or restaurants. How long do you think it takes to make from the digger turning up to dig the foundations and the services to flipping a burger to selling the first burger? What do you think? How long do you think it takes to build one of those?
maybe like less than 3 months, 2 to 3 months.
Yeah,
2
they
to 3
do.
months. That's a good start. Yeah. Any others?
They do seem very, as you say, like it's like come straight out of the box. They all look exactly the same. Those McDonald's drive-through.
Yeah, they do.
So
They do. They are identikit, you know, but so's the food. You know what you're getting. That's part of the appeal, isn't it? That,
yeah, the burgers are the same.
we all you want a Big Mac. You know what you're getting. Not getting into whether it's a good thing or a bad thing. Just and the branding, etc. It's you go into lots of sports stores or clothing shops, and you know exactly what you're getting.
Exactly.
That's not a criticism.
Mate,
so how long do you think it takes to bake one then?
I'd say 4 months from start to
4
finish.
months, 3 months, 4 months. So you'd be quite surprised if I said the norm, the average, is 3 days.
Yeah, that is surprising.
So you'll be really surprised when I say the record from breaking ground to selling a burger is 24 hours.
What's the lifespan of a building like that?
That is, from memory, 16 meters. Oh, a lifespan.
Lifespan, sorry.
Yes. So the longest span, is 16 meters. The lifespan, typically for a McDonald's type structure, is 5 to 10 years. But that's not that the building won't last that long. It's that long before it gets moved, rebranded, reconfigured, etc. And the whole thing gets the rebranded and changed everything again.
I see.
The buildings are permanent structures and will last. Well, a lifetime is a bit of a vague, but 200 years plus is entirely possible. Just because they're made quickly on site, you don't see the month, 2 months, the however many man hours, personnel hours it is to put it all together. A bit like making a car. It might take 40 hours to assemble a car, but there's one car comes off the line every so many minutes, etc. It's that sort of mentality that that there is quite a lot of extra time that the marketing doesn't tell you, because we've got to roll the metal, put all the bits together, etc., etc., etc. But once it's done, once it's put together, it's just like any other building. It's just we've thought about how we're going to move it. So it's still traditional-ish methods. It could be timber frame, it could be precast concrete. These ones are particularly light gauge steel. That's my area, that's my thing. They're the ones that I know about and will be talking about. But once in this case, the light gauge steel is encapsulated in the plasterboard on the inside, the insulation on the outside, and whatever finishes we need to put on for planning, etc. The light gauge steel then stays in a warm, dry, inert environment. So it doesn't really need to be galvanized from that viewpoint, because it's warm and dry. And it just sits there for eternity.
So
galvanized steel. Sorry?
So no galvanization at all then?
No, it is. The light gauge steel is galvanized.
Right.
But my point is that it doesn't really need to be.
Oh, okay.
But tradition, which is a bit weird to say in such an innovative field, is that it's galvanized.
Yeah.
I think it goes through the rollers, etc. The manufacturing process is better because galvanizing zinc-based is relatively soft. It often acts as a bit of a lubricant, which sounds really strange, to the manufacturing process. And if you look at the rollers on a rolling machine, then you will see the pickup, it's called, the deposits of microns of galvanizing over the thousands of meters that they roll a day onto the rollers. Not enough that they change the profile particularly, and it is very soft and yada yada yada, but you do see, and when it's sheared, the ends are cut to length or holes are punched into the steel, the punches and the shears drag the galvanizing over the raw edges so that they are no longer raw and it's continuously protected.
Yeah. Pretty clever.
Yeah.
Yeah.
When you site cut it, site drill it with a cutting disc or a drill, you don't get that because that's a mechanical cutting, drilling, swarf removal, etc. Officially, we need to touch it up with some zinc-rich primer or similar to make sure that it's all protected. And it's more that if it got wet, if there was moisture in there, if it was left out on site for a couple of days before it was covered up and got damp or cold and damp, you would potentially get rust, tearing, staining from those unprotected edges, and that would eventually leach through the plasterboard, through the plaster and into the finishes, the decoration on the inside of the building, which is very unacceptable. And difficult to repair because you've got to take plasterboard off, repair locally, etc., etc. So we make sure that it's all galvanized. It's belt and braces. We're engineers. We're not fashionistas. What is wrong with the belt and braces? You make sure your trousers don't fall down. We're not here to look, a certain way. The building, it needs to be robust. Yeah, the architecture, we have to work with our colleagues and make sure that we consider that side of things, that it's got to be functional, it's got to be, appealing to people. The concrete grey boxes of the perhaps Soviet era, as an engineer, yep, what's wrong with that? It's warm, it's dry, keeps the weather out. But even I appreciate, Philistine as I am, that it looked a bit dreary, a bit drab, a bit. And that's not what we want for society. I'm not saying it should be painted all pink, bright blue, etc., like Tobermory or something, but there is definite value and benefit to the architectural colleagues and the aesthetics of a building, and we should be working with them along with our colleagues on the HVAC and the services. And it's not, my point is that we should not be blinkered. It is not just our job. It's not just the structure. We are part of a team and we should all be working together. And then finally, 2018, I've got to update some of these, I tell you. Ilk Homes opened their factory in Flaxby, which is a tiny village 3 miles down the road from me, vaguely near York, by the side of the A1. It was an ideal location. Unfortunately, they went bust quite spectacularly last year. If you do a Google for them, you'll see that they were on BBC News. Mark Farmer was promoting them. They were the poster child for modular construction, etc. They were partly owned by Elliott Construction, a modular builder, and Keepmoat, a regional developer from Doncaster area. And they did a lot of work. They even rented space at Weatherby Racecourse to store some of their houses and things. But allegedly, they didn't have a big enough, strong enough pipeline of work to keep going. Wasn't involved with them, didn't work with them, so don't know, can't comment. However, I am always amazed, and I'm on record on various public forums as saying this, how any prefabricating company can blame planning as a barrier to workflow for them. I live in a very, I think, very nice house by a company called David Wilson Homes, who are part of Barrett's. And our development has 200-300 houses on it, and there are 4 or 5 house types on the development. But they also mix that up with render, stone cladding, and brick cladding, masonry cladding on the outside. So that gives then 15 house types or looks. And with some judicious planning by our architectural colleagues for the layout of the scheme of the development, the street scene is really nice. There's very rarely 2 houses of the same type next to each other, apart from, you know, the semi-detached house, obviously not counting in that definition, because they'll put 2 latent houses next to each other, but one's rendered and one's clad with stone, etc. You can see the same houses, the same type of developments up and down the country, and they all look fantastic, and they all look subtly different, etc. And they often use local bricks, local stone, as you would expect, within keeping of the aesthetics. But the inside, the structure, the inner walls, etc., are all the same, no matter what the finish is on the outside. And that's one of the joys of modular panelised prefabricated construction, that we can make it look like anything. The inside is one thing, the structure, the plasterboard, etc., the floor joists, but the outside of the building can be anything. It's that's the innate flexibility of this form of construction, of offsite construction. So it always rankles me personally when people say, "Oh, it was planning." So, well, no, like with the McDonald's drive-through eateries, restaurants. If any of you can remember the mad cow disease issues in the early 20s, 2000, sorry, early 2000s. BSE, mad cow disease, was meaning that people couldn't go to different parts of the country. So one example of the McDonald's, they had a restaurant going down to Cirencester or somewhere, and the disease was found, so people couldn't go there. So rather than sending the crew and the building to Cirencester, they diverted it on the motorway back up to Glasgow, and they stopped work on Cirencester and accelerated work on the Glasgow site, because the building was the same. It made no difference to where it went, is my point. And that's got to be the same with housing like this. And these are, you know, nice houses, desirable, etc. Planning isn't the issue, because they're coming up all the time. They're the same on the inside, so then they could be making so many of these houses a week, and it doesn't matter to the factory where they're going. They could be going to Timbuktu, to Ireland, to the UK, it wouldn't matter. So to say that planning is the issue, I think is wrong, is a fallacy. That a factory should be able to have a sustainable flow of work on that basis. Rant over. So what can light gauge steel do? We've got a few examples coming up. This is a 7-story travel lodge in, I want to say Peckham, but it's not Peckham. It's one of the London suburbs. These were concession stands selling T-shirts, food, etc. at the Olympics in 2012. These were subtly different. There were little boxes with this overhanging canopy, which was different in itself, but we couldn't puncture the floor, the tarmac. We weren't allowed to leave anything but footprints and take anything but pictures mentality. So to stop these things blowing away, in theory, and overturning, etc., we put water tanks in the floor so that we'd have sufficient mass to provide the additional friction to stop it moving and stop it overturning. The irony of this was that we couldn't even put a 10mm hole in the tarmac to put the resin anchor bolts to hold it down, but there was a series of 30 or 40 of these around the outside of the arena. But we were told we couldn't put one down for 2 or 3 days because the builders had missed something that they needed to go into the ground where we were going. What have you missed? Well, you see that big torch in the middle of the park? No, the Olympic torch. Yeah, the big one. Yeah. We forgot to put the gas pipe in for it. And this was 10 days before the opening ceremony. It was an interesting job. We also got called in 2 days before the events started. They'd missed a section of seating in the swimming pool. It was a fun job. This was a vertical extension, a rooftop extension, from the 2010s. This, before it became like a popular thing that it is now. This is light gauge steel with some hot roll beams in there, admittedly. And this is the render of it. I never got to see an actual photo, but it's in Brazil. The owner was his company manufactured metal in Brazil, light gauge steel in Brazil. So it was his new family home. That was a nice one to do, quite challenging. This again for the same client. This is a portal frame using lattice trusses. And we've started to do, this was in Brazil for his factory storage. And we've done a business park in the southeast, near Hastings, in the last couple of months. Phases 1 and 2 are done, and there's 3 more to go of portal frames done this way. They're great, but as you can see, the members run through, so they're quite difficult to erect. So it's better to put it all up as one big frame, but that's difficult in itself. So these guys have started to try and push the rafter onto the column, and it's difficult. This is light gauge steel. It's in York, not that far from me. The inside is light gauge steel, the outside is reclaimed bricks, and the steel frame went up so fast that they had to slow down, stop, wait for the bricklayers to keep up with them. One of the features of York is that the buildings have to reflect architecturally the buildings on the other side of the street. So you can end up with buildings with 4 different finishes on 4 different sides if that's the case. That's one of the conditions. So we talk about modular or panelised construction now. So here we have some examples of modular with hot rolled beams and hot rolled posts. You see a mono pitched roof, so it's shallower at one end than the other. But you can also see that we only need supports at the ends and in the middle, and there's nothing across the span. So these are open and forms classrooms. So they'll be 13, 14 meters long and 3.5 meters wide. The limitations on length for modules are transportation limits. The longest we can transport in the UK is, I think, 16 meters, and then it's 2.9 meters just carry on as normal, and up to, just trying to read something at the side of the wall, 6.1 meters we can transport, but we have to potentially move lampposts and have police escorts and only allowed to move at certain times of day and night, etc. So it's something that you as designers, as engineers, need to be considering if you consider any form of off-site prefabricated construction. So these were modular again. This was Panelised. This was a vertical extension in Doncaster, vaguely near the market, if anybody knows Doncaster. It was over an existing roof, and as you can just about make out from these joists spanning front to back, we went from parapet wall to parapet wall on these lattice trusses, front and back, without putting any load onto the existing roof. These are floating houses, or lodges. There's quite a market for this, for holiday cottages, retreats, etc. They put them on floating pontoons, and it's supposed to be extremely relaxing and pleasant place to be. This was Panelised. It's a award-winning school, a national award-winning school for its construction. Won Buildings Award for innovation in school design, I think it was, about 10 years ago now. Leeds East Academy, and being an academy, and without getting into the politics of that, they built a warehouse, effectively a shed, and you can just about see the columns of the shed here. And then within the shed, made these panelised classrooms with mezzanine and etc. So it's a lovely, fantastic building. But the point being that if the academy failed as a business, they would have something, a structure that they could sell on and reuse for something else. The other advantage of these, which isn't immediately obvious, these acoustic baffles, etc., that you can see in the roof and you can't see in the walls, particularly there's another one there and there. When this is the middle of a building site, when I walked into the classrooms and shut the door, the noise was, it nearly hurt your ears. It was so quiet. Yet when spoke and had a conversation, it worked. The acoustic design, the architectural design, etc., was fantastic for this school. Hence, it won the awards. As somebody who teaches lectures, and my wife's a secondary school teacher, just meeting the requirements of the Department for Education on acoustics doesn't really work. There was another school in a similar area in Leeds, and it was just concrete soffits to the ceilings. And yes, it met the acoustic performance, the acoustic requirements of the Department for Education. But as teachers, your voice and the children and any other sound were bouncing off the hard surfaces. And it was really difficult to hear and to teach and to be in. Whereas this was, well, award-winning. It really did work. This is the Doncaster building. Photo of it actually being built. So, what are the benefits of modular?
It's a bit quicker on site.
Yep, speed on site.
And it's repetitive, so you do one.
It's what, sorry?
It's repetitive, so it's like you don't have lots to design. They just give you the reaction points for the supports where you fix them. So like our job as a structural engineer is half, because the modular companies, they usually come up with the the sizes, and then they give you reactions for your supports. We only deal with that part.
Yes, yeah. I'm looking at this from the viewpoint of you are the modular company, or you are working at the modular company, and you are doing the design for the modular company. But you're right. as the main contractor engineer, then yes, you'll just be given foundation loads, and it's far easier for you as a client's engineer. A lot of the work and responsibility is done or taken for you. One of the other advantages is quality of finish, because it often can be, should be prepared, finished in a factory. We've got factory controls. We've got a better, cleaner, safer, nicer working environment. So there's opportunity for things to be done slightly better. Definite advantages from that viewpoint, all of which mean it's producing a better finish, a better quality product.
Adding on to that, could you also make the argument, and like this is just something I've picked up on my time on site, obviously with these modular designs, it's almost like you don't need such what's the word, say like employee training and things like that, so say like including for things like hot works, more specialized skills on site. It's not very necessary when you have modular designs, because it is literally, like as you say before, putting together like a Lego kit. You can have something where it's like literally no welding, nothing like that. It can just be joined together by like any old employee. It is literally like just a big Lego kit, essentially. So yes, it's almost like you don't
absolutely
need to have.
As an industry, we use the phrase de-skilling.
Yes. Yeah. Exactly.
Yeah. That is one of the points of this, of using the factory quality of finish. I'm trying to think of politically correct language, to be perfectly honest.
That's exactly what I was trying to do. You got to take a step back.
We can use less skilled or unskilled staff labour for the putting it together. I've got some slides coming up on this aspect of that side of the automation to make that point. But yes, that is one of the major draws of modular, panelised, offsite construction generally. You probably will see press articles, social media articles about the lack of skilled workers, how the fact that construction is losing staff hand over fist. More people are retiring every day than are coming into the industry every day. So the construction staff population, for want of a better way of putting it, is getting smaller day by day.
Yeah.
But we are told that we need more and more construction, more and more housing, etc. And it feels, according to those reports, that we're going to hell in a handcart, and it's an impossible situation. To which I retort that this hopefully should bring about change. That we've been doing it this way since the Romans, and it's plainly not working because more people are leaving, etc. So let's do something a bit different. And it's getting to the stage now where we've got to do something different. The old ways just aren't possible because there aren't the people there aren't the skills, etc. This is an alternative. It's a viable alternative. It works. The world's got to wake up, smell the coffee, and get on with it. Hopefully the dinosaurs are the ones that are retiring, and the bright young things like yourselves are the ones that are coming through and think I'm not talking a lot of bunkum. See that there is some benefit to all this. So we'll see, won't we? I've got another 20 years or so to go. I've been doing this for about 20 years. Unfortunately, this week, John Prescott died terrible for his family, and it's not pleasant when anybody dies. But I do remember him standing on a balcony on a modular building at a BRE offsite show, the first one that was done in 2003. Stood on a balcony, and I'm not slim as I could be, but he was a bigger chap. Stood on the balcony saying, "This is the future. This is what I'm talking about. This is what we should be doing." When I say, and that was the headline, and I'm thinking, this is brilliant. I've just joined this industry a year earlier. The Deputy Prime Minister stood on my balcony, because I'd engineered it, on my building, saying, "This is the future." What a time to be alive. What a time to join this industry. 20 years later, 21 years later, I'm still sitting here saying, so come on then.
Any minute now.
But, like I say, there's one reason that I do the lectures like this. I do CPDs. I go into primary schools, secondary schools, to try encourage other people to take up the baton, to do this, to see the benefits, to see that it works. It's one reason we developed the software business. But we've got another couple of hours. I don't want to waffle on too much. But briefly, before the break at 11, the software business was, as the Professor said, set up out of MMC. We saw a need for software. We looked. I was talking to the SCI, the chair, the chief exec of the Steel Construction Institute, at a seminar in Leeds. I said, well, why is it not more popular? Why is there only 30, 40 people come to this seminar today, to find out about light gauge steel? And it's not taught at universities at the time. Right. Okay. So that's one of the reasons I got coming to things like this. And also, it's that most engineers, and I'm aware of today's audience, but at the time, most engineers were white, middle-class, middle-aged men. And I'm one of those, unfortunately, or middle-aged and white. And those men don't like to say, "I don't know." They don't want to ask for directions. They don't like to admit that they're wrong. Like I say, I'm myself included. And that includes not knowing how to design in light gauge steel. So architect will come along and say, "I've got this great idea, I want to do this." Oh, I've already designed it in concrete, hot rolled steel, timber, or my other favourite, that'll never work. Well, we've done 30-story buildings this way. What? I've never gone in that, etc. And we decided, Graham Countsman and I, that this was the main barrier, that people didn't know how to do it. So I said, well, come on, then, why the SCI? That's what you do. When they were set up by British Steel, when British Steel was a state-owned manufacturer, and they were given billions of pounds a year to be an intelligent think tank and promote steel as a construction material, because that would be beneficial to British Steel and to the government. Now British Steel are no more, are privately owned, etc. Steel Construction Institute don't have that same funding. They rely on their members. So his response was reasonably, losing the payers to do it. Good point. Somebody's got to prime the pump. You've got to be able to develop this stuff to be able to sell it, but you've got to pay someone to develop it in the first place. You can't square the circle off, can you? And at the time, I was doing some work with the SCI. I was checking their work on Eurocodes, which I'm ED015, I think it is, or ED005. Anyway, it's a design guide on light gauge steel to the Eurocodes, and I'm credited as checking it on their behalf. And the payment for it was to be given a copy of the book in Word, which I then converted into TEDS, which is a package by Trimble that does maths. It's like a hybrid of Excel and Word. You can put A equals 1, B equals 2, C equals A plus B, and it tells you it's 3. Same as Excel, but TEDS also does it with units. So you can add inches to millimeters and what's the answers in miles. And it tells you just on the fly. So I then developed stud checks, joist checks, etc. And we've gone on since then. But I did it in the TEDS environment because TEDS already has a user base and familiar interface, and these white middle-class, middle-aged men will be comfortable and familiar with it. And we've never looked back. So that's why we've got the software, and I'll briefly talk about it and discuss it later. But purely as these tools exist, and they've got some examples of the checks and calculations and things in there. It's anything but a sales pitch. Right, it's 2 minutes past 11 according to my clock. 10, sorry. 2 minutes past 10. If we could all reconvene at 15:15, I will carry on from there.
Sweet.
Okay, I'll see you all in 15 minutes.
Okay, cheers.
I just flicked on to the last few points of benefits of modular. We talked about reduced trades, as in skilled labour, but we didn't mention the reduction in waste and mess on site, so you get a much cleaner, tidier site. And there are reduced deliveries and site traffic because there are less vehicle movements, etc., which can be a benefit to the local area. And as one of you touched on already, potentially reduced foundations. We could be looking at pads, screws, discrete pile foundations as opposed to strips, etc. Although we can still use strips, as appropriate, but there's a potential for reduced foundations. So next, look at the benefits of panelised construction. So here we have a couple of examples. This is the Doncaster one again. It was a relatively tight site. This was, I talked about portal frames for an industrial park. This was like pre-phase one. This is the precursor to the job of the same client. And this was a recreational vehicle, RV maintenance shed. So it was about 15 meters wide with this mezzanine in and quite high to allow vehicles to be jacked up on ramps, etc. But it was speed of access, ease of access, reduced specialist equipment and lifting. With modules, you might need, well, you do need fairly hefty cranes and trained staff and lifting straps and etc. Whereas panelised can be handballing, can be moved in manually. In fact, tomorrow morning, I'm helping on a job which I'm going to show video for in a second to unload. It's just up the road from me and it's coming as sticks, not even panels, that will then be assembled into panels on site. But with panelised, we can still have a reduced build program, which has an impact on revenue in terms of, and one of the advantages of modular is the reduced revenue. Thinking back to McDonald's or thinking to hotels, etc., or student accommodation. One of the financial impacts is that this can be the construction program, build program is reduced overall from it would be a nice idea to opening the doors, selling a burger, renting a room, etc., which has a massive impact on the cash flow. And if we save 10% on the material costs, that's £10,000. Whereas if we can get this open weeks, months earlier, it can be hundreds of thousands of pounds difference that we make. So it can make a real difference to the bean counters, to the client, depending on who the client is. Reduce trades, waste, and mess on site, same as modular. We've got design flexibility because we're not limited to certain sizes, transportable sizes, etc. You've got much more flexibility in terms of design with panelised construction than you have with modular, albeit, and having said that, we can still use modular for the core and then keep the flexibility of design for curved edges, etc. We can be done traditionally. We can do the majority of it in modular and bring in elements of panelised construction, which we know as hybrid construction, a mix of offsite and traditional trades. So it's not we have to do one or the other. We can mix and match these together if that's going to help, if that's going to work. So this next one, not just modules, it's panels. We combine it with a LiDAR scan. Has anybody heard of a LiDAR scan? The laser scan?
Yeah,
Yeah. So we can do the walkthroughs, augmented reality with things like AR Connect, or Connect is a program by Trimble. And using this, you can show with an iPad, iPhone, or other mobile device the client what it looks like on site. They can walk around the site and see where it's going to be. And I have actually on one of the websites, the mess.uk.com website, on the news section, I think it was there. Anyway, we've done a video of that, of the client walking around looking at this building. And I'm going to switch to YouTube in a second and show you the fly through of this. Are you seeing my screen, aren't you now?
Yep.
Did you see rendered fly through by PQS Tech?
Yeah, that's on there.
Yep, right. So this is just off the main high street in Knaresborough, a busy market town in the north of the UK. That was a 2.6 metre wide ginnel alleyway, and now we've gone through a 3 foot wide, metre wide corridor. We had the LiDAR scan done. Nice. And then introduce the model into the scan so that we can see what it's going to look like. You can see the tight courtyard that it's going to be in. You can see the corridor that we've got to get through, and you can see the alleyway that we've got to get to. And this is onto the main street. Quite a busy high street. So we're going to unload bundles of sticks, take them up here through the corridor, and then assemble the sticks, the individual C-sections, into the trusses and wall panels that are required to make this. And it's all going to be, we're going to assemble the floor, ground floor first, and board that out so we've got a working platform to work on, and then build it here, and then cut through into this existing hole, this existing building here. So it'll be a kitchen area in the existing building, a hallway, living room, minstrel gallery with bedroom, and then you'll be able to come out of the door here onto this roof area for like a roof garden. So it'll be a one bedroom social housing type scenario. The client actually owns the house here. This is their courtyard and garden, and they bought this whole building to the right is already social housing, and the plan was to build this, but the developer just didn't. So the current owners bought this piece of land, and he's spoken to numerous local builders who said can't be done, just not possible, access, all the rest of it, not interested. Which is a bit like a red rag to a bull for me, so you can't do that. Right. So here we are. So say tomorrow morning we're unloading the material and we're building it. But we've done videos of the LiDAR scan being done, client walking around. We've got articles on the IFC, interchange file, something, I can't remember what it stands for. The 3D text file, effectively, so that you can see it, rotate it, section it, etc. The structure, and make sure that it's where it wants to be. But using the augmented reality and the tour, and the client, the owner, is in his late 70s, retired orthopedic surgeon, very intelligent man, just doesn't understand construction drawings, and it really irritates him personally that he can't understand, because he is clever. But using this technology, the look on his face, it was brilliant, because the penny's dropped. He understands. He can see where things are. He's been able to look at where the light sockets are, and there's a door in the right place, and etc. before he commits to doing this, which is fantastic and wonderful, and means that we can better explain to clients what they're getting, what we're doing, how it's going to work, exactly where things are. And this whole LiDAR scan and interpreting the millions of points of data cost £500 for the whole scan, for the whole shebang. The video you've seen and everything was all £500. The model's created anyway as part of the manufacturing process for the light gauge steel. So it was just a case then of the detailer, the draftsman or draftsperson, putting that model inside this scan, which is very easy to do, I'm told, for those that know what they're doing. But the effects, the ease of communication. It's one of the big things I was taught as a younger engineer when I first joined, was that we could be Einstein, we can be geniuses, but if we can't communicate those wonderful ideas we've got, those principles, etc., to other people, whether it be to building control to sign things off, or to the client to show what we're doing, it matters nothing. Diddly squat. If we can't get ideas out of our head to other people, not necessarily to a piece of paper now, I mean, looking at this, it's a 3D model, then it's all for nothing. So tools like this are amazing, and it's a fantastic time to be alive and to be involved in the industry when we can do this. If you think Pokemon Go, that's what we're talking about, the augmented reality, the ability to be able to show all this stuff off and interact and in real time. It is just absolutely amazing. We can go as far as automated assembly. There's the AMRC, Advanced Manufacturing Research Centre. They're dotted all over the country. There's one in Sheffield. There'll be one down in London, I'm sure. There's one in Liverpool. There's one up in Glasgow, I think it is. You're going to have copies of this presentation, so you'll be able to get to the white paper. But what they did with their modular robots is they were able to take sticks, like they steel stick sections, top track, bottom track, and studs, and assemble them using a robot. So in theory, or in practice now, we can automate the engineering, we can Then from the engineering, we can create the 3D model. We can roll the metal and assemble it without human intervention. And that's not Rise of the Robots or anything other dystopian thing, or trying to get rid of staff. We were saying earlier that more people are leaving the industry than are joining. So we need to do something. We need to find other ways of doing this. So if we can not replace, but find alternative ways of doing it without the staff that we don't have, which is what this is, then we're finding ways forward. This has got to be a good thing. We can also do portal frames, solid C-section portal frames. This is a relatively new development for us. These are good up to about 20 meters. And that's great and fantastic because over 20 meter spans, hot rolled steel portal frames really come into their own. If you drop below 20 meters, you're limited by the hot roll beam sizes that are available. 203, 254 UBs. I mean, you can get down to 152 UBs and PFCs and things like that. But due to the rules governing bolt spacing, etc., we can't use anything smaller than a 203 or a 254 beam to get the bolt spacing for 10, 12 mil bolts, which is what's required to have the capacity of the connections. So below 20 meters, they start becoming inefficient and heavy. Whereas using tools like this, we're a fraction of the weight and comparable, if not slightly quicker, erection manufacturing times and costs. So that they have a place. 6 meters, 8 meter spans, garages, gyms, etc., and they work. If you go to see the relevant section of the website, you'll see that again we've automated it. The engineering, the 3D models, estimating quotations, the lot. Again, we're not trying to replace people, we're trying to provide solutions to where there are no staff.
And I've got a question regarding the light gauge portal frame design because because when we do it with the normal steel, we design them as sometimes like a plastic frame which sways a lot, and like I assume that the light gauge steel is less stiffer than the normal steel. So how do we control the sways in for longer spans? Like what kind of limits are we looking? Because usually if it's like a brick cladding or something, we got I think H over 200, but I'm not sure how it works with the LGS. Is it plastically designed or elastic or?
It's a very good question. Light gauge steel is all plastically designed.
Okay.
All the ultimate limit state checks are plastically designed. But light gauge steel is generally, and it's one of the things we'll come on to in the next slide, but light gauge steel is generally deflection limited. It's lightweight, it's reactive, it doesn't take much force, whether it be mass, wind, etc., to excite the floor joists. And it's the same with portal frames. It's the deflection that limits the design. Yep. So we look at the eaves deflection and the apex deflection, and we also account for the sway, P delta or lambda crit, depends on which standard you're using. And that then determines the design generally. For a 9-10 meter portal frame, we are looking typically at 200, 250 deep C sections, and they're 3 meters apart. We've got sample calculations I can happily share, send, etc. on this for anybody that's interested at all.
Yeah, I'd like a copy of that if you wouldn't mind.
Yeah,
Yeah,
of course.
that would be interesting
I'll
as
make
well.
them. I'll send them to Professor Savardis, and he can share them.
Oh, thank you.
Yeah, no, that's all part of the service. And yes, has been a reasonable amount of pushback from hot roll steel fabricators because, well, they think we're stepping on their toes. But we, MMC and MES, aren't, because we don't manufacture or sell any of the sheds anyway. And B, as I've said, they are so lightweight and so effective where the hot rolled steel frames are becoming ineffective. So they're an ally of the hot rolled steel portal solutions.
Now, I had a quick question in regards to that. You say the traditional hot rolled steel frames are becoming ineffective. Is that because of things such as like the environmental impact?
Oh, sorry, no, let me just stop you there. I meant
Okay.
below 20-meter spans, they become ineffective.
Right. Okay.
Or less efficient.
Oh, what, for the hot rolled, you mean?
Yes, because you've still got to use a 203, a 254 UB, even at a 4-meter span.
Yes.
Which will also be what you'll be using at 20-meter span.
Exactly. Yeah. So it's overkill essentially.
Yes, that's it. Yeah. They're overkill, but it's because of the detail of the connections, etc. Whereas in the light gauge steel world, we could drop down to a 150 or a 100 mil C section. And we're talking, kilograms per square meter.
Yeah, which is huge in steel design.
Yes, yeah. Absolutely. Okay. The lattice truss portal frame solutions, they can do up to 30-meter spans, and they have their place, like the Mongolian steppes, Afghanistan, places where it's difficult to impossible or extremely expensive to get hot roll steel to. Whereas if we've got a coil of light gauge steel, we can manufacture so many different things. And anyway, but they weigh about 3.5 kilograms per square meter.
Yeah.
But 35 meter span portal frame that way, the columns and rafters are 2 meters deep.
Right.
But you can do it. And it's 3.5 kilograms a square meter. So that's the payback. That it's ridiculously light. It's possible to do it, and one response is then that okay, we've got 2 meter deep walls. Let's make them into shelving. Let's make a feature of them. Let's not let them be a problem. We're engineers. We're looking for solutions, aren't we? Not barriers.
Yeah. So and also, I suppose, if you've got like spans that big, deflection will eventually become a problem. No matter how good your beam is, it's going to become an issue, isn't it?
Yes. Yeah.
Yeah. Okay.
Yeah, and we limit the deflection to height of 250, span over 180, height over 180 for cladding at least. So we are limited, and we do take those into account. And that's almost like a separate lecture in and of itself. Time-wise, that's all. So I'll move on to the rest of what we need to design for, etc. Self-weight, imposed load, fire. Next, if that's okay, just conscious of the time, it's not got so much time left. So we need to think about self-weight and imposed load. One of the advantages of light gauge steel is the material itself is lighter weight, but the wall finishes, floor finishes, are still the same materials, as in we would still use a 18mm chipboard OSB for the floorboard, but this is as opposed to a 150mm concrete slab, which we still can use, but sort of defeating the object of light gauge steel. And the imposed loads of 2-3 kilonewtons per square meter are the same, irrespective of what material we make the building from. The same with fire, wind, and acoustics, particularly, they're the same irrespective of what we make the material from. Vibration is more of an issue for light gauge steel because it's lightweight. It's easier, as I mentioned or touched on earlier, easier to get it excited, easier to get it moving. And once it is moving, there's not so much mass to dampen it out again. So it's something we need to be aware of and consider, and we'll come on to shortly. And because of the vibration, deflection, height is a consideration, but it's also a consideration for other buildings, obviously, but it's slightly more so for light gauge steel in terms of the deflection, etc. So, self-weight and imposed loads. What floor finish we're talking about? What ceiling finish? And what's the use of it? Is it a domestic property? Is it, domestic residential? Is it offices? Is it storage? Is it industrial use? The uses have a dramatic effect on the loads that we apply, and they'll also potentially have an impact on the finishes that we're looking at. For example, a hospital would have higher imposed loads because of what it is, beds, etc., equipment. It might also have tighter deflection limits. If it was an operating theatre, you don't want the floor vibrating and the surgeon's hand moving, do we? But we might have heavier, harder floors, tiles, etc., for cleaning compared to carpets. But then the floor finish affects the vibration, the deflection. So there's a lot to be thinking about when we're specifying a joist in terms of what it's going to be used for, what it is that we're designing. It's not just a floor joist, it's a floor joist for whatever it is. Thankfully, there is some guidance in. There's a design guide called P402 by the SCI, by the Steel Construction Institute. It's P402, light gauge steel in residential construction. And as part of it, it discusses the vibration requirements for floor joists, which again we're going to come on to on the next slide. But the deflection and the vibration are partly determined by the floor finish. And to that end, it has tables to help us design the floor. It talks about the acoustic performance, airborne and impacts, and gives an indication of fire rating. What it doesn't tell us is weight or what type of floor it is in terms of the deflection criteria that we'll come on to, say, on the next slide. So what I have done with their blessing, permission, knowledge, is to enhance these tables to include definitions of what these floor types are, which again we'll come on to in a second, and some makeups. I've listed the weights based on the makeup that's in there and etc., so that we can make the design slightly easier. Again, it's one of the things that I will send to be posted on your server. It's a 2-page A4 PDF, just a visual guide and it also included in the software as part of the notes to make it easier for users to see and remember the figures that we're talking about. So, floor design, we have 4 deflection criteria: 2 static and 2 dynamic. And as I mentioned earlier, strength is rarely the limiting factor. So for static deflection, we have the maximum deflection of a single joist subject to dead and imposed loads, span of a 350 or 15 millimeters, whichever is the lesser. And then we also have check the deflection of the joist, span over 450, but based just on the imposed load. Okay, so they're fairly standard, and they're to do with the look of the finishes, so we're not going to get cracking, etc., in the ceiling and plasterboard. The dynamic deflection, the natural frequency, the feel of the building. I know it sounds a bit touchy-feely as an engineer to be talking about the feel, and would feel like we might be wandering into the realms of architecture, etc. But I'm sure you've all walked on floors, and it just feels, you can feel like a vibration, a tremor, a movement. The absolute worst example was Marines, naval soldiers, in their berths, their beds, barracks, on land, feeling seasick when they laid down. Some of the roughest, toughest people on the planet who are trained, designed, call it what you want, to live on boats and fight and everything, feeling seasick, laid down in bed. Comes from the floor vibration. Humans goes back to a very primeval cave dwelling thing. When we lay down, the cochlea, the inner ear, gives us our balance, feels vibration, and it feels vibration more sensitively when we're laid down, so that when you're asleep, if you heard predators padding round, you'd have felt it more sensitively when you were laid down and asleep and at risk than when you were stood up and walking. So when these Marines were laid in their beds and the floor was vibrating just enough to set off the inner ear, they felt seasick because of the movement, because of this inner ear thing. That was just before I joined the industry, and immediately after that, right, we're not having this happen again. That's ridiculous. Some research work was done, and we now limit the frequency of the floor to less than 8 hertz by applying the dead load plus 20% of the imposed load and limiting the deflection to no more than 5 millimeters. And then we also look at a single joist with a 1 kilonewton point load and limit the deflection to 1.7 to 1.2 millimeters, as you can see in this table here. And I kept babbling about the floor type, the floor configuration. The SCI had missed out in the table. They hadn't classified these floor build-ups into these floor types, so that we didn't know which of these amounts of joists we could share this 1 kilonewton point load over, the load sharing. The idea being that as the 1 kilonewton point load pulls down the joist, because of the finish to the joists, the joists either side will be affected, and we will share the load. so that it's not the one joist by itself. So this is the way of factoring that in. This is listed out in an SCI P402 and in NHBC Chapter 610. NHBC are a UK warranty provider, structural warranty provider, and as such they provide design guidance on what they need a structure to do to comply to meet their requirements for a warranty. So it's well documented, it's well proven, and if we build the floor this way and fasten the floorboards down properly, which we'll cover in the next slide, so that it's built robustly, the floor will perform as it's supposed to, and nobody will feel seasick, you won't feel the vibration as you're walking across it, etc. So it's all doable and nothing scary. And incidentally, our software obviously includes these checks, etc., and does that for you. So, floor joists are need to be fully restrained by the finishes when the boards are attached to flanges. 230 millimeters in the centre and 150 millimeters at the board ends. That is ridiculously tight. 150 millimeters or 6 inches, or roughly, if you hold your hand up, finger and distance between your finger and small finger and thumb tip. Imagine having to fasten the floor joists, the boards down those centres. It's back-breaking work, but that's what we need to do. When you go to a site, and if there's a problem, this is one of the first things you need to be looking for. Are the boards fastened down properly? Because if the boards aren't fastened down, if they aren't as specified, if they aren't of the correct thickness, the joists will not be restrained. The joists will be free to move, will bounce, and the board will bounce in between the joists. Because that is 9 times out of 10, it's the people have used the wrong thickness board, and it's the deflection between the joists, the board deflecting between the joists, it's the problem, not the joists. We typically stick to 400 and 600 centres because of the plasterboarding that goes underneath. We use the plasterboarding for acoustics, for fire, and for general finishes. But they come in 1200 by 2400 sheets. So we need to stick to those grids, and they also need supports at most every 600 millimeters, so they don't sag and fail, etc. Hence,
I've got a question here. So,
yes.
if the main idea is to make sure that the floor joist and the board doesn't deflect like independently or differently, why don't we use a nail guns to just put them in place? Why do we have to screw them? Like,
it can be a nail gun, it can be screws. I personally like the idea of a layer of glue or a layer of isolating tape, self-adhesive tape, and the screws. It's partly to do with the performance of the floor on the day-to-day use of it, but it also matters, and this diagram is taken from P402 discussing fire performance. So when in the event of a fire, we need everything fastened together properly. The 1 or 2 fire tests that I've witnessed, and one of them failed because they hadn't put members, straps along these joints here that I'm highlighting, not where the joist is, but between the joists. The board, after 5 minutes, got so hot that it was then peeling away at this joint. And then after 15 minutes, the board had fallen off, and then there's no fire protection. So the joist started to get really hot, started to deflect more, etc. It makes a massive difference to the fire performance. Now, the fire is not something that happens every day, obviously and thankfully, but it is extremely important.
Yeah, that makes sense. Thank you.
No problem.
Yeah.
Thank you for asking the question. At least we know people are still here and that you're paying attention. So, as I just mentioned, other floor considerations, because it, as I keep trying to say and get back to, we're not siloing ourselves. We're not just structural engineer and that's it. And we are, and that's what we're doing. But it's not just about the structure. It's not just about the engineering. It's about the whole thing together, isn't it? The architecture, the services, the everything. So we've got to think about the fire, acoustics, thermal, and most importantly, or not most importantly, but one that's very easy to forget, is it buildable? Is it manufacturable? If we come up with a design that's fantastically light and, you know, cost pennies to in terms of metal or material usage, but is, in the worst case, impossible to manufacture or slow to assemble, or then we're going to lose the job. I often work, and the industry often works on the 80-20 rule. 80% of the cost is the labour, 20% is the material. So if we make a 10% saving on the material, we've saved 2% on the job. Whereas if we increase the labour by 10%, that's 8% of the cost of the job. So if we make a 10% saving on material, but make it harder by 10% to assemble, we've cost an extra 6%. So it's not working, is it? My point is that we, as engineers, as part of the team, have to think about the whole. The acoustics, the fire, the assembly, the manufacturing. It's not just.
That's a really interesting point, actually. The saving on the labour in relation to the materials, because obviously, I mean, I don't know everyone here, but like a few people here are in construction already. Like the margin of profit on jobs isn't massive. We're talking like 1-2% anyway.
No, it isn't, and this is again one of the issues that we're trying to address with this. The lack of staff, the profit margins. No other industry would accept the 2 and 3% profit margins that construction does.
Exactly.
No other industry. You look at pharmaceuticals and things, and it's 200 or 300%, and the rest.
So sorry, just to build onto that. So this is why you're trying to like propose using light gauge steel for more, because you can essentially do the same thing with even less material in an industry we're already trying to reduce the amount of steel we're using anyway for like recycling purposes.
Yes.
The difficulty of getting it, things like that. Okay, so in regards to that then, because I'm seeing like new build housing going up absolutely everywhere I look nowadays.
Yeah.
And you hear a lot of people always saying things like, oh, they don't build them like they used to and stuff like that. Now, is that because literally some of these things are already being put into practice now? So they're like literally trying to get more out of less stuff on some of these, like you said at the beginning of the lecture. Say if you've got a housing development that's 300, 400 houses, if you could save 10% across every single house, then obviously that saving's massive. Is that something that's starting to come into play more now?
Yes and no.
Right.
So my house was very traditionally built, is timber floors, timber joists, block work, masonry on the outside. We have a very talented, he's now 20-year-old at university playing guitar. When we moved here, he was 13, and you could hear a fly break wind upstairs. Not to mention him and his bank of amps. The acoustics is shocking, but it's acceptable. It's what we're sold. Without sounding like a conspiracy theorist or anything at all like that, it's just this is the reality. This is what is acceptable, and you know I've bought it. I'm one of the ones complaining about it, and I'm not saying that light gauge steel is the panacea, or is the answer, or using light gauge steel would have improved the acoustics, etc. at all. I'm saying that as engineers, it's something we should be thinking about. I'm saying that as engineers and members of society, I think it's better use of resources, materials, and labour. I think if we had panelized this, I mean, this house was 3 months late. We bought it off plan. Using these methods and knowing that a house will come off the production line every hour, as Ilk did, there'd be no excuse. It would be there on time. It would be fine. The stairs needed repairing 2 or 3 times. There's this issue, that issue. That wouldn't happen if it had been made in a factory and quality control, etc., was better and with less skilled labour. I'm conscious of not falling into politics or pushing my opinion on or putting my opinion forward on some of these points while still having a healthy debate. I'm trying to be balanced.
Like I say, it's just something that I was wondering. That was all.
I'm just very conscious of not saying that one thing is definitely the way forward or not.
I get what you mean, mate. Say no more.
Yeah. It's something for us all to think about. If you all leave today and go out asking the questions, I've done my job.
Right.
That's all I can do. Whether you or the industry come back and say no, the blockwork and timber joists is the way forward, is the best answer, then fine. That's it. That's the answer. And I'm, mature enough to accept that and carry on. But I think there are alternatives. I think that we need to be, as an industry, think about different ways of doing things, and this is a different way of doing things. But as part of doing things differently, we also need to do things differently and think about other trades, other people, the clients, the homeowner, everything, not just siloing our actions, is one of the points I'm trying to get across. But like I say, I very, very passionately believe this is the way forward and this is the best way of doing it. But I am, open to being wrong and to having a conversation and discussion about these things, not to force people. Mine isn't the only answer. Mine isn't the only way. I'm not the Mandalorian. I'll quickly mention, so we've got the break coming up. Just quickly touch on wall studs. Again, SCI P402 and the document I'll share has examples of wall build-ups with acoustics, fire, nominal performance, etc. We need to think about the effective length, how high it is, and how we're restraining the top and the bottom. If there's an eccentricity of load, as in if it was rain screen facade, etc., or stone cladding, if it's 300 mil, 30 centimeters away from the face of the stud due to insulation and cavities, that can start having an impact, additional bending moment, etc. Do we increase the number of noggins to reduce the effective length, or do we increase the gauge? Because that would reduce the stockiness, the slenderness of the profile. Again, we need to think about fire, how we're dealing with that, how we're protecting it. Acoustics, speed of construction, speed of assembly. We talked about the labour a few minutes ago. And equally, is it a modular or panelised system? It's like in the very bottom picture here. This could easily be a modular building, two modules, one either side, and you've got that double wall construction straight away for the acoustics, the load bearing, etc. If it was a panelised and you've got this sort of construction, or this one, you might have floor joists from both sides loading onto it, so you've got twice as much load. It's that sort of thing to think about. And then this is an example of the software, just to show that the values that we put in, loads, etc. An example of the member checks, so you can see the checks that we're doing, the buckling resistance, overall local capacity checks, etc. And then we'll talk about modular versus panelised, the benefits, advantages, etc. At 12:15, 11, when we all come back for the last 15 minutes or so, if that's okay.
Yeah, that's fine.
Yeah, so sorry, what time was it again you wanted us back?
11:15.
No worries. Okay. See
About
you
9
soon.
minutes. I'm sorry I've overrun slightly, but
No, that'd be
we'll
fine.
keep you all going too long. And for the record, if anybody wants to have a conversation about anything I haven't gone into too depth about today, I'm more than happy to do it. Like I say, I'm just conscious of as a lecturer to not be forcing my opinion onto people, to try to give you the facts and let you make informed decisions. But I'm happy to have a conversation with anybody about any of it.
Of course.
Okay.
Yeah, no, I'd be interested to get a copy of those calculations, to be honest.
Yes, like I say, all that's going to be sent through, shares, etc. You'll all have my contact details on the last slide.
Yep.
And I'll make sure that you got all that. So if anyone needs to speak to me after the event, I'm here. I'm available. It's not just a one-time thing.
Okay, cool.
No problem.
Right.
I'll
see you shortly.
See you all at 15:15.
But
sorry, it's not too much of a break. Okay. Are we all ready to carry on?
Yeah, we're all good.
Brilliant. So, modular versus panelised. The image was student accommodation in Durham. It's showing modules being lifted in onto obviously pre-made foundations, services, wastewater pipes, etc. are all there. And this took a month to build. I've forgotten how many beds of student accommodation, but it was 3 stories. There were 4 or 5 blocks of it. It was quite a big job, and it's quite quick on site. It was quite close to a railway line, and in fact, if you're ever on the train going through Durham, you'll go past the accommodation just before you get to the station. But the drivers are speed on site. It was fully finished. The first person through the door had been a student that had paid however many £1,000 for the term. We need to consider access. Can we actually get modules in? and can we transport them from the factory where they're made to there, and any other drivers as opposed to people moving the thing, actual, you know, requirements and reasons for using modular. So when it comes to lifting modules, this is again was the same site. You can see 1, 2, 3 floors, and the modules are all bagged up to keep them warm and dry. But there are as many solutions as there are manufacturers when it comes to lifting. The Lola regulations, lifting regulations, mean that you have to use tested equipment, lifting shackles, lifting eyes that are hard stamped and certified and tested and tracked. If we use temporary lifting points, as in a stud that is extended through with a service hole in for the lifting point, that's a temporary lift. It's used once and then cut off. You don't need to have the testing, etc. So there's that advantage to it. But you have got more work to do on site to cut it off, to remove it, etc. We need to consider connectivity, how we fasten one module to another, because this is obviously an issue. We can't have differential movement between module side beams, etc. But equally, fastening 2 or 3 millimeter pieces of steel together side by side that are able to move vertically or potentially move vertically. Another name for those is a shear or scissors or guillotine. So you've got to be careful. You don't want people putting fingers, limbs, or any other appendages in there and risk losing them, having them chopped off. So you need to find ways of connecting the modules together safely. But it's also got to be robust, and there's a lot to think about. Hence, there's as many solutions as there are manufacturers. Over the years, I've seen dozens, not hundreds, but dozens of different solutions. And there hasn't been one yet that I have seen and thought, that's it, perfect. We can stop looking. They've all been brilliant for 95% of the problems, but not one has covered absolutely every problem. And I thought, that's it, we can stop looking now. So if you're looking at a PhD and things, and I know Costas, Professor Tsardis, is doing work in this area, there are opportunities, in my opinion, to come up with some fantastic solutions for this. And the other big one, and this picture illustrates it really nicely, is weather resistance. We've got to keep the modules dry, weather tight. We don't have these fantastic finishes applied in a factory, so they're all really well done and etc. And then they get water damaged or wind damaged or anything else damaged. So we need to think about, whether it's modular or panelized, how we fasten walls and roofs, walls and floors to floors and roofs to walls. And there are two, not schools of thought, but two general definitions of platform or balloon. Platform, as it says, is where the floor sits on top of the wall. So you'd have a wall stud for the ground floor, wall stud for the first floor, and a joist in between. And we need to run a very simple check to make sure there's no localized crushing. If there is, there are solutions like putting a C-section wall stud at the side of the joist to stop it crushing so that you get continuous load path. Or if we use balloon construction, which is what the illustrations showing, the floor joist, roof joist, sits inside the walls, typically on hangers. So we can see this dark blue line on top, comes down and underneath. That's known as a Z hanger. And those Z hangers can be as long as required, as long as can be manufactured, typically in a press brake, and they are 3-4 meters long. I am aware of one that's 16 meters long. It's actually 2 8-meter presses working in tandem, but they could be a meter. The point of the Z hanger is that it's as long as it can be. The joist can be sat on there in a group all together and then spread out on site, but they're all level. If we use individual joist hangers or individual Z hangers, we've got to line and level every one and space out while holding the hanger in place, and it becomes a lot more complicated. So these are some simple solutions. We'll skip the video, just so we'll run through a very quick design example. We want to wind up fairly quickly. We've got another 10 slides to go. So we need to think about wind load, self weights, deflection, trimmers, etc. Okay. So wind is quite critical to light gauge steel because it's lightweight, it's deflection limited, the horizontal lateral loads from the wind are quite critical. We tend to use at this end something called Breathe, which is 1980s, 90s program, so it's quite old, based on a NASA topographical survey from the shuttle, which shows quite how old it is. But it shows height above sea level, density of buildings, etc.
Yeah, very good program.
Yes, yeah, we like it and we sell it through MES, but that's something else. But it gives accurate wind analysis. Now that can be a double-edged sword. If you just look at the map and say hull 30 meters a second, boom, distance to sea looks to be so far. If you use Breathe, and Breathe is actually it's 35, not 30, and it's not 5 kilometers, it's 2 kilometers, that can be disadvantageous to the design. It can increase the wind load. But as engineers, it's right or it's wrong. It can also mean that we can get lower heights above sea level, we can get further from the sea, lower wind speeds, and it can work in our favour. But it's right or it's wrong. But calculating the wind load is quite critical and very useful. Horizontal members, whether they be roofs or floors, is it a C section or a lattice? Going back to the labour and the materials, a C section can be heavier, more material, but it's quick and easy to assemble and put together. Whereas a lattice truss could use less material, but take 10 times as long to assemble. So there's those aspects that we need to consider. And there's also the consideration of if the client only has a 100mm machine, which is not unreasonable, then they can't make a 300mm deep solid C-section joist. They have to make lattices, and that's the end of the discussion. But we, as engineers, designers, need to be aware. We also need to consider the load. Sorry?
Question regarding the C beam. For example, when we deal with like, let's say, portal frames, but we don't want to do lattice or truss, sometimes we pre-camber them for the dead loads. Is it something that we could do in light gauge as well? When the deflection is more
I know what you
governing.
mean. Yeah, I'd say no, because manufacturers, try very, very, very hard to make sure that the C-section is straight and true and not curved. Having said that, it is entirely possible to produce a bent C-section, a curved C-section, if the rollers and the machine isn't set up properly. But you really don't want to be doing that, and the machine manufacturers do everything they can to make sure that's not possible and doesn't happen. However, in caravan manufacture design, because they are extremely cost sensitive, then yes, they do look at pre-cambering side beams, etc., to then deflect to a level position when they're loaded with the self-weight. But as we've talked about already, light gauge steel is generally deflection limited. It is sensitive to deflection. It is sensitive to vibration. So by pre-bending, even if it was a third-party bender service, you run the risk of it being so close to the limit of design that it feels wrong. Like if you walk into a caravan and the doors are a bit rattly when you slam it, and you can hear people walking up and down the floor. All the things that we really don't want in a permanent building. That we do our very best to engineer out of a permanent building. They're all acceptable in the caravan industry because it's just a caravan, it's a temporary structure. So it is possible to do it, but we try really hard, or we try not to do those things because of the risks that they then bring into it. And it's a 10% saving in the material, but the material's 20%, so it's the cost of the job, so it's a 2% saving overall. There are far better places to be looking, like improving the manufacturing process, in making it the assembly more efficient, etc. If we save 10% there, that's an 8% saving again in the overall cost. So by the time we've pre-cambered and spent a bit more on it, pre-cambering it, we could easily end up losing money or costing more than we would have saved by just going up a gauge or putting the joists closer together, etc. One of the things our software does is work out the weight per square meter per linear meter to make that side of things a little easier. It doesn't tell you the assembly times because we don't know that. As an aside, I do have some information on that because one reason I fell into light gauge steel is as a production engineer. I started off as an apprentice making packaging machines. I'm a chartered mechanical engineer, and immediately before joining the light gauge steel industry was working as a graduate production engineer. So it's something I'm very, very interested in, and possibly why I consider the manufacturing, the assembly, the labour side more important than the material weight side. I don't know. That's maybe something to take up with a psychologist or a behaviourist.
No, I think that's a fair point. To concentrate on something that makes like actual difference than saving a few kilos on the steel rather than saving a few times in the labor. I think that's something we should look into as well. No, I understand.
Yes, well, that's my belief, but I know I was sponsoring a PhD at another university some time ago, and they developed some wonderful new profiles, etc. And they were far, far, far stronger than traditional C-sections, but the design they produced, like for like, were heavier than the traditional C-section because they were less stiff. The strength was improved, but the stiffness had gone down. So it's very easy to lose your focus if you're not careful. And I've made some massive improvements, yeah, but in completely the wrong area, and it's made the job cost more. It's unfortunate, but it's a great example from my viewpoint of concentrating on the right area. So studs, we think about the loads that we apply, centers, the number of floors, because that obviously can have a difference. I, on an aside, tend to run the stud design every 3 floors. So on a 6-story building, I'll design the 3rd floor and the ground floor studs. I wouldn't design the top floor, 5th, 4th, 3rd, 2nd, 1st, and ground. I just do 2 designs because of this economy of scale, of manufacture, of assembly, of detailing, and the saving that I make by running the design at every level. The benefit to return, the cost benefit, isn't massive by the time the detailers change what they're doing and the people assembling it and erecting it have had to concentrate that little bit more, and etc. It's generally not the case that it makes that big a difference. Stud design, though, wind load, the deflection checks, and whether we need them as the frame designer or the next engineer in the chain needs them, the foundation loads. And again, our software separates it out into SLS and ULS, imposed and combined loads to make it easier for marking up the foundations, etc. Progressive collapse. Isn't a majorly real issue for light gauge steel, in that the way the whole thing's built. If you notice, this plate here is a good example. The amount of fixings that are in there, and if we consider the fixings from the joist into the Z hanger, and the Z hanger into the thing, and stud to stud sideways from panel to panel, there are non-scientific examples, but real world practical examples of people trying to dismantle exhibition stands. It might take 3 or 4 days to build the stand, and then by 5 o'clock show's over and everybody's got to be out by midnight for the next show to start. So people pull wall panels off, pull etc. And the building just stands up with 2 walls missing, and the floor might sag a little bit, but it's not collapsing. And it's unbelievable to see until you stop and look in detail and think about how many fixings are fastening it all together and how much capacity each fixing has. A 5mm tech screw, self-drill, self-tap screw, in 1.2mm gauge material, which is about the thinnest we'd use, 5mm diameter, has a capacity of 3.2 kilonewtons, which is 320 kilograms. If we go to 1.6mm gauge, which is fairly heavy, we go up to 3mm, but that has 5 kilonewtons capacity, or 500 kilograms of capacity. That's just one screw. So in this sketch here, we've got 4 screws. So we've got, I've worked this out before, 1.2 tons of capacity on either side of that, assuming that the strap, reasonable assumption, that the strap has the same capacity, if not more. So Progressive collapse is a thing. It's something we need to consider. The load that's applied to it, the member centres, the class of the building, as we put in bold. So a two-storey house would have one progressive collapse requirement, and a five-storey hospital would have another. The construction method and the connections, which inherently come through the construction method when we're talking about light gauge steel. So it's things to think about, but it's not a real issue for light gauge steel. Openings in walls, lintels. We need to think about the floor and the roof load, the width of the opening, because deflection is the issue. And if you look at the bending moment formula, W times L cubed over EI, Young's modulus and stiffness, W times L cubed times E by itself times I by itself. Length, L, has 3 times the effect of anything else, doesn't it, in that formula? So the area increases, the loads increase, but if the length increases, it's having 3 times the effect compared to a 10% increase in load or a 10% increase in length, width of the opening. The length's going to have 3 times the effect. So then we need to think about how we're making them, what the deflection is, ultimate limit strength checks, and then the fixings, and what's supporting it, reactions at either end, what studs, joists, trimmers, etc. are carrying those openings. Racking, there's a recent new guide from the SCI on racking design, P437, which actually increases the amount of brace bays that we need compared to the SCI's old method, but that's, by the by. Building dimensions, so how much area is having a window load applied to it, what the stud height is and the profile for the lambda crit checks, sway checks, and how we're doing the bracing. Is it K bracing? So a series of diagonals that look like a capital K, or lattice truss between the studs? Is it X bracing, so cross flat bracing, which in my opinion doesn't work? Again, P437 discusses it at some length. P437 suggests that we fasten the X brace into every stud as it goes past, but again, in my opinion, that's not right. That's sort of cheating. The maths doesn't do that. And as we put the flat strap down, if there's any sag, any wobble in and out of the page, so to speak, by the time we've got it taut by stretching it top to right, diagonally, we've then got into second order effect territory of the amount of distance that takes to take up the slack. Again, there are blog posts about it, and there's lots of information in P437 about it if anybody's interested. Or we can use the sheathing boards, whether it be plasterboard on the inside, cementitious board on the outside of the studs, between the stud and the insulation, plywood OSB. That's what we use for timber frame. There was a design guide called ED002 by the SCI and Trada back in the 80s, referencing testing that they did, or the British Steel did at Shotton, I think it was, and formulas that they've derived from that, empirical formulas based on fixing capacity and stud spacings and height, etc. So there are methods there. We've got the sway check to do, the lambda crit P delta. and uplift. And uplift can be the killer. Whether it's the old method or the new P437 method, the uplift forces in a K brace are in the region of 20 kilonewtons, 25 kilonewtons, which is 2 tons to 2.5 tons. And while they're not massive in terms of a strip foundation or a screw pile, if we were trying to use things like beam and block foundations, and you're not going to be screwing into the concrete beams because they're nigh on impossible to drill into, you'd be fastening to the blocks, and a 2.5 ton block or even a 2 ton block just doesn't exist. So we're then having to mobilize, try and pick up a large amount of bricks, blocks to withstand that localized uplift, which is where X-bracing and sheathing come into their own. So there's work to be done on that, in my opinion. The next one to talk about is fire. Following Grenfell and the Hackett report and all the other things that have followed on from it, we're told to test, 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 test. Here's a great photo of a fire test for the floor. One that's failing at this stage, but otherwise it's quite boring to see. Floor joists, great, easy to test up to a certain span based on the size of the furnace, etc. But when it comes to wall studs, we have similar limitations on height, but more critically on the load that we can apply, the vertical load. Now, this is where it gets to be, in my opinion, dangerous, because the more load you apply to a stud and then set fire to it, the more likely it is to fail. That's kind of obvious. If a stud would carry 100 kilonewtons and we apply 99 kilonewtons to it and then set fire to it or apply heat to it, it will soften up. When it gets to a certain temperature, 250 degrees, metal gets annealed, softens, loosens its strength, and then it fails the test. So the more load we apply, if we applied 105 kilonewtons, it would fail straight away. If we apply 90 kilonewtons, it might last 10 minutes. If we apply 10 kilonewtons, it'll last all day. So some system manufacturers literally apply 10 kilonewtons. Actually, 14 is the figures I've seen. And then declare they've got a 90-minute fire rating, which they have. But only at 14 kilonewtons. And we were just talking about K-bracing applying 25. The stud itself can carry 100. We're engineers, we're making it as light as possible and as efficient as possible, so we're squeezing every last drop out of it. So we might be applying 99 kilonewtons to it. Then that means, according to the testing standards, 1365, that the test is invalid based on the loads that we're applying in the design case, which is a real problem, especially as the test rigs can only apply about 30 kilonewtons, 33 kilonewtons, period. So if we're looking at bigger studs that can carry 200 and 300 kilonewtons, why bother testing? What's the point? It's just not realistic, which is a huge problem. But then, me being me, I don't like to say we've got a problem and what do we do. There are solutions out there. There are existing standards, British standards and European standards, that we can calculate the member capacity to already. They're about 10 years old, so it's not a new thing. What those standards don't do, and where they're headache continues is they don't tell you how long it will stay safe for. So there we have to rely on some element of testing, or board manufacturers giving us effectively U values so that we can calculate how long it takes for the heat to transfer through to the studs, and then for the stud to get to 350 degrees, and we calculate the capacity of the stud at 350 degrees, etc., etc. So there are things we can do, but we need to think about board failure. When does the board fail? Because yeah, you've got a 60-minute fire rating. That means that the fires only come through the cold side of the wall, not the boards on the hot side. How are the boards fixed? We talked earlier about floor joists and having to put those fixings at 150mm, 230mm centers. Consider, is the test realistic? Because although fires are quite rare and they're not a day-to-day occurrence, when it happens, and we want to be sure that people are going to be safe, the buildings are going to be safe, but more importantly, people are going to be safe. And we can do, like I say, calculations as an industry. It's not something that MES sell, although MMC Engineer, we can offer that service, but again, not a sales pitch. Acoustics. We design the structure to be as stiff as possible, but stiffness means that sound gets passed through very easily. So that's a problem. So we use soundboards and resilient bars, ways of stopping the sound getting into the studs in the first place. Resilient bars are brilliant, are fantastic in a lab, but it's very easy for installers to get it wrong, to drill through the resilient bar into the stud and effectively bypass it. And when it comes to pre-completion testing, it's failed. And you don't know where it's failed, how it's failed. It's difficult to find. So the simplest thing is to use things like soundboards. We can put insulation, mineral oil insulation between the studs, which helps dampen the vibration, the sound transmission. But if we put insulation between the studs, it can affect the fire performance, not by much, but by 3, 4, 5, 10%, reducing the fire rating times, go from 60 minutes to 55 minutes and things, which doesn't sound like a lot, but it's the difference between a pass and a fail. So there's these things to be considering and thinking about.